Let's talk about some physics. I found this article yesterday. World's first 3D simulations reveal the physics of exotic supernovae. I'm going to cover this first, this idea of what an exotic supernova is. So a supernova is something that you've probably heard of, most people have. Supernovae are a relatively well understood phenomenon, for mainstream, that is. It's very well understood in terms of the physics, but most people know what a supernova is. So you have a big star. Towards the end of its life, it starts to fuse very heavy elements. Eventually, it reaches iron in the core, and iron has a very specific property where it costs more energy to fuse iron than it gives back after fusion. As you get up to iron, fusing heavier and heavier elements, your returns on that process are lower and lower and lower. So fusing hydrogen into helium gives you the most energy, and then fusing helium into whatever is next gives you less, and then going from there to there is less and less and less. As you fuse into more heavy elements, you start to get less energy return until you hit iron. Once you hit iron, it flips. Once you hit iron, you start to lose energy every time that you fuse. And since a star is kept up by the radiation pressure from the fusion reactions pushing outwards against gravity pulling inwards, when you start to fuse iron, a lot of that energy gets lost, and now you can no longer sustain the size of your star. You start to lose a whole bunch of radiation pressure, and all of that plasma that was fusing other stuff rushes into the center because gravity no longer has anything stopping it, slams into the iron core, reverbs back out, and it causes a giant stellar explosion we call a supernova. These only happen in certain types of stars. Other stars will just die in other ways. Like our sun is not going to die like this. Our sun is going to turn into a red giant and eventually burn itself out. This happens with larger stars, bluer stars. These explosions are way brighter, they last way longer, and a lot of other things are very strange. That's why they're called exotic. And we don't understand these super well. We've been trying to understand why these things are so much brighter for a while now, and we've gotten some of the way through that. This actually was done back in, I think, March, and it only got published recently. We actually have just done the first three-dimensional simulations of a giant star exploding. Now, before this, we've done one-dimensional and two-dimensional simulations. You might ask, well, how do I take a three-dimensional object and reduce it to one dimension? Well, you just look at the radius, right? So you start at the core and you work outwards, literally in the radial direction. You just pick one tiny little line slice and you do all the physics in that line. And that's fine. It usually works pretty well, but what it loses is it loses all of the interaction in any of the other dimensions, right? Because obviously we live in a three-dimensional world, and when we're dealing with plasma and fluids, you need to account for things like currents, and you need to account for turbulence. All of that stuff is very important. So we upped the ante and we went to 2 dimensions, and now we're talking about a slice through the center, a big circular slice, and this gets us some of the way there, but still doesn't account for all of the dimensions that these things could be moving in, right? If you had just a sphere of water and you were trying to model it, 2-dimensional slice is not going to give you all the information because you're missing things that are rotating around outside of that slice. If you have a piece of paper like this and things are moving in and out, you lose all that information. So you need 3 dimensions. And for a while, we thought that 2-dimensional was going to be good enough. It would answer a lot of our questions, and it didn't. Now we understand why. This was done by a bunch of researchers in Taiwan. I believe they were using some of Japan's supercomputers as well. This paper is very dense. I'm not going to talk about it too much. I'm just going to show you some of the pretty pictures and explain as best I can. The first plot that I want to show, this is showing us the gas density at different positions in the star at a certain time, 250 days post-supernova beginning. This is basically the radial profile of the star under each different type of simulation. So we've got 1-dimensional simulations, 2-dimensional simulations, and the new 3-dimensional simulation. These values up here with these kappas, these are what are called the opacity. It's how easily photons or electrons, depending on what you're talking about, can move through the material. A higher number means that you are more opaque. It means that you have a denser medium. They ran a few different simulations with different opacities. It's not super important for what we're talking about right now. The important takeaway, though, is if we look at the 1-dimensional simulations, which are the solid black line and the dotted black line, you'll notice they have one big peak right here. This peak is effectively what we would consider to be the shock wave. So all of the stuff rushes into the iron core, it hits the core, it bounces back out, and we're watching that shock wave extend outwards. So at 250 days, it's at this point in the star. We see a specific shock wave that has now traveled out to a certain point. What we lose in the 1D simulations is pretty clearly seen in the 2D simulations, which are these two blue dotted lines. We see that there's this structure here. So in this simulation, with this first blue dotted line, we see one big hump, two big humps. And then in this other simulation, we see a bunch of structure over here. So there's something missing when we do a one-dimensional simulation that starts to become revealed in a two-dimensional simulation. If we do a three-dimensional simulation, we see two very, very clear bumps. We see two shock waves. We see a double shock. This is where a lot of the secrets are hiding. We can actually see that better in another plot earlier. These are effectively the same thing. So we're looking at gas density, the darker, the higher density. And these red dots and arrows are all radiative flux. So this is how bright the thing is and what direction the photons are being released in. But we can very clearly see there's the outer shell, which is expanding, and this other shock wave coming towards it. And if we look a little further, so this is at 77 days. If you look a little further, at 157 days, we can see those two shock waves have now started to actually intercept each other. This back one has caught up, and then they combine a little later. And after combination, they have a lot of weird effects. So you can notice when we started off over here, this is pretty spherically symmetric, right? This looks like a sphere, or at least a quarter of a sphere, right? Even here, this inner shockwave still looks a lot like a sphere, or a circle in this case. The second we start to combine them, we get these weird effects. We get these weird peaks and valleys, and we start to lose all of that symmetry. This is where the secret physics lies. We can also see that in these plots. It's the same thing. We're looking at gas density. These are comparing two different types of simulations. We're looking at this left-hand plot. Again, we see these two different shockwaves that come in together at once. All of this to say that these three-dimensional simulations are effectively necessary to describing the things that we see because of these different effects that we get. If we don't do a 3D simulation, we don't get these two very well-resolved shockwaves. And we're pretty sure that those two very well-resolved shockwaves are what are causing a lot of this really interesting stuff, the brightness that we're seeing. If we take a look at the brightness plots, which I don't remember where they are, hold on, let me find them. Here we go. If we take a look at the brightness plots, we can see that these types of supernovae go really, really bright and then stay really bright for like 300 days. They have a huge bump, which is higher than most supernovae will go. And then they stay pretty damn high for a long time. Like, we're talking on the scale of years. Most supernovae are, days, weeks, months at most. These things last for a very long time, and this is part of the reason we think why these further shockwaves and these asymmetries. This plot is also gorgeous, though it's very hard to sort of talk about what it means because it's only one slice at one time. This is a slice of the three-dimensional simulation at a certain point in time that's showing us four different things. Each quadrant tells us a different thing. So we've got the velocity of the stuff moving, we've got the radiative flux in the bottom left, we have the temperature in the upper right, and the gas density in the bottom right. For our purposes, what this tells us is it shows us the structure. We can see these weird asymmetries on the edge of the radial distribution, really of all of them, right? You can see those asymmetries everywhere. They're on all of these plots. But we can also see, if we really look in on these areas, on the temperature plot and on the density plot, we can see there's structure in here. Look at this black line right here and this one right here. There's another one down here, some strong ones in the center, all the curvy stuff on the edge. These are all types of, you can call them currents or turbulence. That's where a lot of the key is. A lot of the evolution comes down to these different turbulences and turbulations and all of that good stuff. That's what makes this as bright as it is for so long. And we can see it in here too with the gas density. Look at all this structure in here. You've got these little pockets of higher density inside of this low density region. You've got this stuff on the outside. There's a lot of really cool stuff happening here. This is just one simulation, and this took millions of hours of computing time. Like, we're talking, I think, 15 million hours, if I remember correctly. Sorry, 5 million supercomputer hours. It's a lot of time, like a lot of time. I think this is pretty cool stuff. We'll hopefully see more about this. I think in their conclusions they were talking about wanting to do more, but it takes a long time to do this type of stuff. These simulations take 5 million hours to complete, so even if you're running in parallel, they take forever. But it's very, very cool stuff, and hopefully we'll unlock some of the information about how we got some of the heavier elements in the universe through these types of exotic supernovae explosion, which is a very, very cool concept.